but this is not true for the hair couplet. So we take the best from the structure, taking by the structure a way for representing the solution, taking by the structure a basis of function for representing the problem. And this is for continuous space. For discretized space, for finite element approach, for million of components given by an aircraft model or spacecraft model, you have the eigenvector as equivalent concept. And so if you take the base of the structural eigenvector, the mode of vibration, you can take this basis for represent the problem, including the aerodynamic. It's not forbidden, absolutely. Okay, if you use that basis for representing only the structure, you will discover that the problem is quite diagonalized, decoupled, decoupling. If you do this, including the aerodynamic, you will be able to discretize the problem, but the equation you will obtain eventually will not be decoupled. And you can see this in the next minutes of lecture. Okay, in this practical case, just let me give to you what is the case of eigenproblem for the beam.
Professor, sorry, you can see the blackboard, and if you could record the lesson also. Thank you.
I did. It is currently recorded. Okay, please check.
Yes, but I can see the blackboard anyway.
I don't know why I did. Excuse me. Can you hear me?
Yes, hear you, yes, but I can see the share of the screen.
Okay, okay. Is now correct?
Yes, thank you.
Okay. Okay. For the present case, L phi equal to lambda phi is EI phi n fourth derivative plus m bar phi n second derivative plus k phi n equal to lambda n phi n. This is the eigenproblem for our actual structural operator L. Plus, do not forget the boundary condition. And the boundary condition are the simply supported beam boundary condition. And the solution, in this case, are the following. Phi n of x is equal to sine. If you solve this, then you obtain this. We could do this. It is an exercise in structural dynamics. I will not do exercise now. So, sine of n pi x divided by L. And for lambda, you can, if you assume this for phi, it's easy to evaluate lambda. Just put this sine function inside here, here, and here, and you can easily verify that lambda has to be necessarily equal to EI n pi by L to the power 4 plus minus, because we have to derive the sine function 2 times, and so you have a minus sign, so you have minus n pi by L plus kappa. Okay? This is the eigenfunction, this is the lambda function. If you, we will need to evaluate the module of this eigenfunction, which is the integral of sine to the power 2 pi n by xl to the power 2 dx from 0 to L, and this is equal to L by 2. Okay? And you have just to apply the Prostapherisis formula to this square of the sine here. Okay, now we are ready for applying we are ready to transform our PDE problem into ordinary differential equation problem. Okay? And we have to perform a double step. First, we assume for the solution W this. Note that this is equal, not almost equal to n from 1 to infinite phi n x. These are known functions, sine, blah, 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 blah. By new unknowns, we have as a new unknowns this time function. This is the original unknowns, these new unknowns. Okay? This is the first point, and then substitute to the equation. To PDE equation. The PDE equation is this equation here, remember. So now we have to substitute, and we can do this in the other, whiteboard. We have a first part, which is the structure operator applied to, we had the summation of structure operator applied to phi n w n. In fact, this LS part is a part including the green term here. This, and this. This is the conservative of structure operator, okay? Applied to this when you assume this important position here. In this position, we have a combination of orthogonal functions. Therefore, this is not an approximation. And we are spanning all the space. So these series are actually converging for any time. You have a set of defined coefficients for any time t. You're just a frame of a movie, frame. For each frame, you have a set. Your set of orthogonal function is representing your function, and in any frame, you have a new Wn value. Okay? So you are substituting, this is the conservative part, plus we have this is the part associated to the damping. And we have the part associated to the structural damping. Excuse me, aerodynamic damping. No, excuse me. This is the aerodynamic part. This is accurate theory, fundamentally. Plus this part is the aerodynamic damping as well. And finally, the inertial force. So I have essentially substituted into this equation here at the beginning the position here, this position here. Okay? And this is the first step of our procedure. Substitution. Assume this and put inside the equation. Second part, and this is our new version of fx equal to 0. Second part, project f onto phi n and put each projection to 0. This is equivalent to put each component of capital F to 0, because we have demonstrated that this is equivalent to put Fn of t equal to 0. Because of an dependency, the dependency of and orthogonality of phi allow ourselves to represent the solution and to represent the equation. We have two things to do by the eigenfunction. Okay? So project f onto Fn in order to obtain Fn equal to 0 for each n from 1 to infinite. Okay? And so write together this projection of f on phi m equal to 0, and look at our equation now. We have this equation, we have to project this on, but before doing this, we have, look, we have projection of phi m, comma, now we have to write our equation, because this is f, and I have to write this